In the automotive industry, commissioning times decline steadily, model cycles become shorter, and the variety of models is increasing. To ensure that systems are commissioned on time, virtual commissioning is becoming increasingly important. Our portfolio at Siemens has a variety of several tools for different use cases. For the example of line level, my colleague Sebastian Schisselbauer already presented a video on plant simulation. On cell level, the focus is usually on the process in the cell and the interactions of actuators and sensors. When considering a body shop cell in the automotive industry, we're usually talking about a robot cell. Especially for these application areas, it's important to ensure motion control of the robots relative to the mechanical system and other robots as well. Mechanical damages in these environments usually cause high costs and additional effort, an example for repairs. Especially during the commissioning phase, it happens again and again that two robots collide with each other or a robot smashing its tool against a steel girder. By using Tecnomatix Process Simulate, you can carry out detailed robot programming, simulate robot processes, and verify robot logic. Through the simulation on my computer, I can avoid precisely these kinds of situations described before. With Process Simulate, you're perfectly prepared for real commissioning. Through the connection to TIA Portal, PLC Sim Advanced, as the virtual PLC, and Process Simulate, you can carry out virtual commissioning with real PLC and robot program code. The goal is to evaluate the control program and HMI system, as well as to test motion of the robots using collision monitoring, for example. In the following, we prepared a demonstration of what was mentioned last to point out how collision monitoring can be performed using only little effort. Process Simulate offers the possibility to create collision monitoring automatically. We select the processes that shall be monitored, in our case, 2 welding processes, and start our demo. Here you can see the collision of both robots, or rather of the welding tools. With the automatic interference option, the volume surrounding of the robots is calculated automatically, which is required for collision-free motion. We now select the welding process and choose the automatic interference option via the Robot tab, adding the 2 welding processes with a single click. The volumes of the individual robots are then calculated and displayed. Focus is on the collision between 2 or more robots, as well as on the collision between robots and other objects, like a safety fence. The created volumes are now displayed under Motion Volumes on the left-hand side of the object tree, and I can display them in the 3D visualization. Calculated volumes are shown by the blue markings. The volume of the welding tools on the left-hand robot is displayed on the left-hand side. The volume of the second robot is displayed on the other side. If you hide both in the object tree, you can see the overlapping collision volume of the 2 robots, that is, the area where the motion zones of both robots overlap. This describes the zone where collisions can occur. Next, we can test the interference queries and see the details of the previously performed calculations. The location displayed first describes the last location before the collision area is reached. The second describes the first point that is reached after exiting the collision area. If we look at the OLP command on the first welding application, we see 2 different locations. These locations are relevant for the following calculation of collision-free robot motion. Next, we have to supply the robot with logic. I'd like to demonstrate this to you based on a robot. We open the Robot Signals editor and add 2 signals to define the zones. For this, we'll need 1 input signal each, in our case, 2 rec zone, and 1 output signal, in our case, 2 rec zone OK. These signals are relevant for synchronization with a second robot. Nothing else needs to be done at this point. Now we have to link the previously created inputs and outputs in the OLP commands. We start with the first location. Here we'll add an input signal with add, standard commands, synchronization, set signal. We select the previously created input and set it to 1. This means that for this location, the zone is reached. The result can be observed in the displayed window. Next, we'll add the command which is used to query our output whether the zone is occupied. We repeat the step for the other location. We define the zone to be 0 and then query whether it's clear, respectively 0. As you can see, the procedure is always quite similar. These steps also need to be carried out for the second robot. Up to this point, these were the necessary steps in Process Simulate. Now we'll switch to TIA Portal in order to create the logic on the controller part. The same signals are required for this. As you can see, I've already added the 4 variables with identical names. To integrate the logic into the robot process, we'll have a look at the associated graph sequence. Therefore, I have to query the corresponding inputs and outputs. The process is similar to the previous steps in Process Simulate. In the transition shown, we ask whether the zone of one robot is occupied and the zone of the other robot is clear. That means not occupied. So far, quite logical. Next, we'll define the action in our graph sequence chain, in other words, what to do when the transition is fulfilled. In our case, the to-rec-zone OK output is triggered. The robot is now permitted to move in the zone. This step remains active until the robot exits the zone again. Normally, we'd have to repeat the task for the second robot. Logic creation is now complete, and we can download our TIA Portal program into the PLC Sim Advanced Virtual Controller. In the following step, we switch back to Process Simulate and start the simulation in Line Simulation mode. To start the control program, we'll use our HMI visualization and, in the first step, carry out an initialization to reset all values to the initial state. Then we start the simulation. The sequence of the process can now be observed in the HMI visualization and, of course, also in Process Simulate. Let's see what happens and whether or not there's a collision. What's different from the first time? The robots are now welding one after another, so that one robot welds first, while the other waits until the area, the collision zone, is clear. Collisions no longer occur because Process Simulate calculates the volumes of the robots and their associated tools in the background and prevents a collision. By using Process Simulate, you'll save time and money while optimizing your commissioning phase.
Siemens, ingenuity for life.